So what are we going to be doing today? We're going to go ahead with the multiverse stuff. Basically, what we want to do is I want to start actually coding the Qubit. I've got an idea, so I think it's going to be easy. Anaconda PowerShell prompt. So we'll just go to our Quantum Intuition workspace. And turn on the Jupyter notebooks. That's the video. So I'm looking for the paper, and yeah, basically publications. Maybe here as well. Find the latest publications. This is the thing. Yeah, exactly. So I kind of realized so we find the optimal training trajectory over 8 years for 52 assets using quantum-inspired algorithms. I think that's properly phrased, because I think it's easy to get tricked into believing that like this thing with 8 years and 52 in terms of the amount of data, that this is something that kind of the quantum computer is responsible for to kind of process all this data. But at the end of the day, it's not these what matters, right? Like, because the algorithms are really running on the actual forecasts of that data, right? That's what matters here. So okay, so we're here. So we're gonna have to go to workspace, and we're gonna have to go to portfolio optimization. And did I change anything here? Is everything? It's everything up to date. So we'll probably do Jupyter notebook, because I want to start here, and I think I'm going to create a new notebook because the one that's there is basically I kind of have used it for. Why is it taking so long? The one that I've been using there was for when I was playing with the Chicago quantum paper. And so what we're going to do is we're going to go to what was it, like page 3 or something. Yeah, exactly. So we're going to be, and I'm playing with Epic Pen, by the way. I'm playing with these. Maybe that's what's making the whole thing go slow. So am I happy with the color? Can I change color? I can change color. This guy here. So we're going to be working on each of these components. Will be basically what I will do is I think that for each of those I'm going to kind of make a function that builds the Qubit. And then I'm going to start like by just having like those variables. Basically, I'll just have them initialize them randomly, I think. So the returns, the forecasted returns, these I probably what I wanna do is I wanna generate asset data randomly and then calculate the covariance. And then this was what was that? So this was the this was the transaction costs, right? And so here the lambda was calculated. What was lambda? I think it was some sort of the coefficient, the optimal parabolic coefficient for the approximation that we're trying to make. So I'm going to try to sketch those things, and then kind of, fitting this with real data is going to be sort of a next step. Which, yeah, I think it's going to be interesting. How we're going to be implementing the last block in here? But let's see what can we get done today. Why hasn't... Ah, so it's actually running. I don't know why is it like going so slow. It's probably these. We're gonna create a new. So we're gonna create a new notebook. We'll call this notebook Multiverse Portfolio. So slow. Multiverse. I'll just portfolio. Multiverse, and then so we're basically going to be oh, and I actually have to finalize the installation of the D-Wave of the D-Wave SDK stuff, but we'll basically be building these. Let me see if I can just put this side by side. It's going to make more sense. I think it's going to be easier. I'm going to select these, and so first we're going to be first let's kind of generate some asset data, right? Like we said, what I wanted to do is I actually wanted to do 3 assets. I think I'm gonna do with 3 assets. So maybe we can just start by initializing. Like we'll probably have to add some imports in here. Well, I have to import NumPy. So like what is the best way? It's like import as np, right? Like yeah, NumPy as np. So I'm gonna probably do these, and we'll actually have some more imports in here. Inputs and stuff. So, and then generate random data. What we want to have is generate random data set. So what I want to have is we're going to have like asset data, right? So we're going to have, but is it we're going to have like sort of, yeah, we want to have data, and we want to have like the forecast as well. Now the question is the covariance here done on the forecasted data, or it's done on the actual historical data? I think it's done in the historical data, based on the historical data, not like on the covariance. That's like, because you're not going to predict what the covariance is going to look like. That doesn't make much sense. So we still have to create the but I guess those are going to be, you know, whatever prices, right? So we're going to have like so assets, and that's basically going to be like, you know, an array was like a matrix, right? Like and so random sampling, how random is random? I don't care. Random seed. I just want to random matrix. Just want to create a random matrix. An array of the given shape and populated with random samples from uniform distribution over 0, 1. I don't necessarily want this to be between 0 and 1, but like, okay, so 3 by 2, right? Like, so it creates basically 3 columns, okay, 3 rows and 2 columns. And what I want is np random rand. Okay, so what I want is np random rand. And I want like, what do we do? So we do 3 columns, and rows like we do what? I don't know. Let's say a year, so 365 days. or let's try to do the same amount of data, 8. Now let's just do 1 year, so 365 days, and we want like 3 columns, right? Print assets. Yeah, okay, cool. So we have the data. So we also want to have, so we have assets. We have the forecasted return. Now that's going to be like, we're going to have, so let's define some constants. We're going to have, because we have the different, like here down, when you go down to the experiments, they exactly, so these are the parameters, n, nt, nq. So we're going to find n. So what was the n? N was assets, exactly. So basically that will be n. So and that's going to be 3. And then nt, it's going to be the number of time steps. So we're going to keep it to 2. And nq, I mean, we can use, let's build the excess. Why not? That's the basically, yeah, let's build the excess case. So an n tot is basically n times nt times nq. And so we're going to have the asset data being generated like these, the forecasted return. So the, okay, well, let's define k equals 2. And how do you usually, k prime, whatever. So the forecasted return, it's going to have to be for each t, right? So, but we don't want a matrix necessarily. What we want, or we can have a matrix, but the cube is going to have basically what? So it's going to have 6 times 6. It's going to have to be a 6 times 6, right? Because there'll be 6 qubits that we need for these, if I remember well. Yeah. So you're going to have like a 6 by 6 matrix. Is it true? 3 assets. Yeah. And so the forecasted return could be then, I'm literally going to have to, so I'm literally going to just say like the forecasted return is going to have how many rows? It's going to have like n t rows, like, you know, one for each time step, and then it's going to have like n, right? Forecasted return, cool, for each asset and each time step. Now, what else do we need? So we need that's page 4. Let's go back to page 4. Page 3, actually. So we need to calculate the covariance and stuff, right? So this is the one. This is the sign over here. Now the covariance. This is the covariance matrix, right? I guess. So what we have to do is, well, this is the n. It's an n by n matrix. It's the assets covariance at time t. The assets covariance at time t. So actually, this is really we're gonna have to have 2 matrices, one for time t equals 0, one for time t equals 1. So basically, we're gonna have to have do I it's basically, covariances, right? And then you kind of have like, do I need to declare these, by the way? Play array. Just want to have an array creation. So, okay, just like that. So it's basically, actually, I would say that this is the way I'd go about it is I'll just make hap that, and so we have like it's not defined. Oh, NP array. I'm stupid. Equals NP array. So basically, that's how you do it. And so those are the covariances for each time step. Then the forecaster returned. That was each row. So that was each row one. Yeah, okay. So it's kind of like the rows. And what else do we need? So we need the. So how do we calculate the? Where's the equation? How to calculate these? Okay, so now we need the lambda, but we also need these delta in here. So we need this delta. This delta is going to be what? How do we calculate these transactional costs? The best metrics of transaction costs at time t that is compatible and realistic with market conditions. So we need transaction costs at time t, and the transaction costs are for what? Like to kind of between assets? Is that we have like a transaction, so be also n by n, I think it will be the same than the covariances. So you'll have like tx costs. So at each time t, like a matrix with costs between asset, like 0 and 1, 0 and 2. I guess that's what this means. I'm not so sure though. Polynomial. What are these transaction costs? How are they defined? The transaction costs are typically a percentage of the transaction, whether buying or selling assets. They can be expressed in terms of unnormalized weights. The transaction costs are typically percentage of the transaction. So if you, I guess if you want to take from one asset and then invest in another asset, I guess that would be not polynomial because of self-value function. So this is approximated with the parabola in the considered range, with these being the best metrics of transaction costs at time t that is compatible with and realistic with market conditions. And so this is roughly these. What? Okay, I don't know. Those deltas are basically, it's basically the I think that's something that it's actually part of the calculation, right, of the cubo, because that's where you're gonna have the, where do I have this pen? That's where you're gonna have the so you're gonna have your, like, you know, what is the size? That's where you're gonna have the sort of the x, like the t plus 1, and then kind of minus the x in time t. So what we just need is, we need this lambda, because this is going to be then part of the way they were calculating the actual cubo. We're going to be doing this multiplication and then all that squared. So we need to come up with this lambda, and this lambda, it's going to do. So this is a function of the transaction costs. That's the way that I understand this. Is it? Because we're approximating the function with. Alternatively, we could introduce ancillary qubits. No, blah blah blah. We choose to approximate equation 9, the parabola. Okay, that being the parabola. And so I'd have to find that coefficient. The differences between WT. I'm not so sure. I'm not so sure how to do that. I probably maybe need to just unpack these rather than, right? What do I need? I mean, lambda, I can make up lambda. No. I don't know, to be honest. So the objective function, which accounts for these costs in terms of normalized weights, is given by these. Since n correlates times t and t plus 1, the percentual transaction costs are not polynomial in the variables w and t. Because of the absolute value function, this could limit the applicability of some quantum optimization methods. To get around this problem, we can tailor expand the absolute value in a similar way to the expansion for a step function. Alternatively, we could introduce ancillary qubits. We choose to approximate equation 9 by a parabola in the considered range. Equation 9. So that is that portion in here. Okay, that's then a parabola that you're approximating it for, and then so that is roughly this. So what the delta here of WT is the is this absolute cost, right? Like of the that is essentially the variable at the end of the day, right? Mm. So we basically have so we're basically gonna have that you know, this is the variable. Uh, yeah, well, actually, I don't. So these would equivalent. Would be the equivalent, right, of like t plus one, right? Like in my case, it's just going to be like w sub one. So it's basically I think it was like one over k, and kind of in this case because we have nq1, I think that was just basically square squared. I think that was 2 to the power of 0 in this case times, and then it's the actual variable, right? Of like, let's ask 0. I think it was like this, right? And so this means you know, basically, and one, that's just, you know, one term, and then the same for like x1 and the same for like x2, right? So that will be your vector. And so what we'll have to do is we have to expand these, and so we have to say the transpose of this vector times this matrix times, like, you know, those three elements in here. Yeah, exactly. So you'd essentially here have like 4 times like k squared, like k is 2, so like, yeah, okay, so that plays neatly because that means they just things cancel out. And so you just basically will have x squared, x sub 1 squared, and x sub 2 squared. So that's what you're going to have. But essentially, I believe what we can do here is we can just ignore these because for the cubo this is not relevant. So essentially, what you will have for this particular case is, but we should probably compute that anyway. Like this means this is what I'm doing by hand, right? Like, because that is really what. Sorry. Yeah, that is really what that is replaced with, right? Let me see. Yeah. So it's 1 divided by k times 2 to the power of q, like the sum of 2 to the power of q and then the actual variables. So so that was correct. Now, I guess my question here is, like, I'm curious to see how would you automate, like, how do you automate like the creation of the actual equation, right? Like, if you because for higher Qs, then you'd have more terms in here, so then it becomes trickier, because then you have like 2 to the power of 0, x sub 0 plus 2 to the power of 1, x sub 1, and so on. And this is all kind of squared. And so you need to calculate and expand these terms, and to actually get the final QO. I wouldn't know how to programmatically do that, I think. Well, at least I wouldn't have a smart strategy on top of my head, because I don't know really how to deal with equations in Python. But we'll discover soon, because we have to work on I want to start attacking this last part today as well. So, but basically, for our particular case, we can reduce these to these, basically just have this simple vector. So what that all means, to be honest, is that the transaction cost matrix is the only thing you need. Because then you're going to have like x0, x1, x2 as being the transpose, the actual transaction costs matrix, and then you're going to have like x0, x1, x2, and so what you're going to have is like, yeah, basically these times these, like this is the way this works, right? So also become one cell, yeah, and then yeah, and then you just do the thing. But still, I'll have to actually, I have to build that. I really have to. How do I do that? Because now I'm at a point where, like, that I know how to build. So let's put it this way: so our QO matrix, right? Our QO matrix. Let's call it Q, or just QO. It's gonna be basically MP. I don't wanna. How do I initialize like a? So it's an array. Initialize numpy array to zeros or something. It's gonna be at 0. Like let's just numpy zeros shape. Okay. So it's gonna be just this is just to get something now up and running quickly. But like I would assume this is maybe you know it needs to be n times it needs to be n tot times n tot, right? So this needs to be defined in here. And if I print these np, sorry. There you go. So that's going to be the cube at the end of the day. That shape at least. And so I can generate these things like easily by, for example, let's make a function that gives us these, right? So this would be, so we'll make a function, we'll call like def, like the, I don't know, returns, it's a keyword. Can I call it q1? How do I define functions in functions? Python functions. It's def, right? And it's yeah, just like that. Okay. the parameters are going to be basically it's just a forecasted return for the first component of it, right? And the yeah, the forecasted return. That's it. I don't need anything else. And so what I want this to do is kind of like we initialize a cubo, like a Q1 cubo, like that, and then we're basically saying that just goes to the diagonals, right? So basically because that's the, I keep forgetting, numpy iterator matrix. Because there's a way you can do that. I want to just iterate over these and then say for each I want to basically put it in diagonal, in the diagonal. That's it. So so essentially the 0 0 goes to the 0 0, right? The 0 1 goes to the 1 1. The 0 2 goes to the 2 2. And then 3 2, etc., etc., etc. So can I just say like numpy that's really what I want to do. Construct a diagonal array. Okay. So there's a function for this. That's cool. What is this doing? Or construct a diagonal array. I want arrange 12 reshape 43. What does this do? NumPy. Create a diagonal matrix. That's what I wanted to do. That's where I was, right? Fill diagonal. There's so many functions, like but that fills it with an actual single value. No, okay. Actually, you can give it an array. Let's see what it does. What if I give it like let's say Q1 cubo. What am I doing? What am I doing? Fill diagonal. Fill diagonal. Q1 cubo, and I'm going to give it like the forecasted return. And I'm going to say return these, and now I'm going to basically call Q1 with like the well, that is the matrix M. I'll just call it actually just to, or it's fine like that. And so I'm going to be calling it like this, and I'll just basically print it. Okay, looks like it worked. 0.9, 0.35, 0.30, 0.5. Okay, that's smart. Cool. So this is basically the first step, right? Well, I would say -1 times this. That's what we have. We want this to be. Oh, but we don't want the zeros to be minus. Or we don't want the other ones to be minus. So I think. How do you do that? I think you can just do like these and then say where bigger than 0. Or something like that. Is it correct? Valid syntax. NumPy multiply matrix by condition or something like that. This is where to specify the nowhere, so it's not what I want. Multiply matrix elements for condition. Okay. Sure, though. Ah, well, okay, I know. That's the way. Probably then you just return Q or something like this. X. How do you do that? Do it like this. I think it's easier if I just do like that. There you go. So that's the first part. Then the second part, then the second function should return us this thing here, which basically what this means is that what we should be doing is we should probably be populating some of the non-diagonal elements with because we're gonna have some quadratic terms in here because of the way this is multiplied. Okay, so this is where the first challenge comes in, right? Like that's a constant. We can make it up right now. That's fine. And then we have these, of course. And so how will we go about these in a programmatic way? That's what's be like, because I want to make it as generic as possible, right? Like I want to be able to then sort of change my parameters in here, and you know that would still construct something that makes sense. So the first part is easy because it's just the return goes into diagonal like that. The next term, like how do I do this? Like would I just what this essentially means, right, is you know, take this constant, that's all fine. Then take the transposed of like the vector, which is basically, as we said, it's like 1 over k squared, and then the basically, you know, that expression, right? So 2 to the power of 0 x0. Ideally, would be more components to it, but that's basically it. And so I know that, like, for this particular case, that just translates to like having like x0, x1, x2, but I want to have that like generic expression in here. You know what I mean? Or if I just iterate over, because essentially what this is telling me then is that then if I have the covariances matrix in here, I'm gonna have like the different elements. And if I have here, like if I actually would construct these and then actually have the multiplication, then I would really have would I have everything that I need? No, I would not, right? Because that obviously would be only for step T, and I actually have to do this for the 2 steps. Okay, so that even becomes trickier because I'm not so sure. So the Hamiltonian is the sum over T across the time steps, right? The problem that I have with these, no, I don't have any problem with these because I'm mapping to a cubo. That's the thing, and I'm trying to do this programmatically as like sort of by a bit like, you know, going component by component, but maybe there is a way to express equations in Python already that would allow me to map that easily. Just by then having the coefficients or kind of querying for the coefficients. So is there a way to handle equations in Python? Otherwise, I can't figure out a more generic way to approach these. Python equations. SymPy. Let's see. So you have an example symbolic math expression is x squared plus y squared equals z. SymPy. SymPy is a Python library for working with symbolic math. Before SymPy can be used, it needs to be installed. Inserting SymPy's kind of prompt. Can't install SymPy. So So importing the symbols. Conda SymPy. This is what I need. Now the question is, so you'll have to, so you create the symbols, and then you can build expressions. Then you can insert numerical values, but we don't care about these. I want to query the coefficients. SymPy query coefficients. Oh, there is actually something. That will be easier, I think. So you're building the whole thing, poly from expression, and then degree returns a list of degrees of degree. That returns a degree least coefficients, the leading coefficient of f. That returns 2, 1. But how do I? So the division. SymPy compute polymer coefficient. No. SymPy is a SymPy. Okay, coefficients. Here you go. So we have the symbols, blah blah, coefficients. I want something like that. Yeah. Exactly. That's also what I want. Poly. Huh? There's a method, ask coefficient section, but it seems this doesn't work in the way I want. This way is to use poly. What is poly? Okay. Okay. So, but poly like comes with SymPy or? Proceed. Seems like this was installed already. Python poly. Because then I just have to, oh, NumPy poly, no, SymPy poly, yeah, okay. What's the typical way SymPy is imported? Just SymPy, maybe SP. Okay, cool, but it's there, right? So if now we'll just say import SymPy as SP, and what we can try and do here is something like, so okay, so how does SymPy work? So you have an expression. How do you do that? So you create symbols, right? Okay, so x, y symbols, x and y. Okay, I like that. So if I do like these, and then I do like that, and then I do print expression, then I'm getting symbols is not defined. Well, SP symbols. Ah, cool. Okay, perfect. We'll comment that out for a second. And if I'm doing then SP poly, so what was that, SP poly? Sorry. These coefs. Okay. Coefs. 2 and 1. I like that, but it's still not giving me what does all coefs give me. Coefficients, but that doesn't tell me to which element they belong, right? Like I want to be able to have that dictionary. Collection of questions can be handled with poly, and then separation of the monomials into dependent and independent parts can be handled with expression as independent. So you have to collect, and then you're doing what? Dictionary I as independent. Use poly so you have the coefficients, but like that doesn't tell me. Simpai. Oh, so there's something like this. I can give it Simpai coef. Go. Okay, I like that. So I can actually give it the. So I can actually say I don't need poly, so I can just say SP coefs, and then I can say I want a coefficient of x in expression. No. What is 2? What is 2 for? We are able to find a coefficient of variables in mathematical expressions. What is n? What is this? Simpai doesn't have. It's coef, okay. No? Simpai coef. Oh, well, no, yeah, SP. Core simplify. So, how the heck can I find these? Maybe that's not there anymore. SimPy get coefficient. I don't want to extract all of them. I wanna get something that would be even better, right? Because I would be able to just I know what the coefficient is. Maybe that is indeed with poly. So what did I have before? Coef of x. Get coefficient. Poly. Come on. SimPy, get a damn coefficient. It's gotta do something. It's gotta be something like these. Oh. Maybe just like that? No, no. SimPy coefficients. Oh, so you actually can do this. So if I just say expression coef of like x. Okay. Of like y. Okay. Cool. What if I have like x squared, right? What is the, so I print the expression. That will not give me anything, but if I do like this, that would actually give me 2. Okay, makes sense. Okay, I like that. Good, that actually is something I can work with. Now I gotta create enough symbols. I'm gonna create enough symbols to codify the problem, right? So this means if I have so if I have basically so we're gonna have to kind of, you know, iterate. So basically kind of like I'd say for each time step, right? To be honest, not for each time step. What we need to do is first we just need to build the equation for the expression for these, right? So you know, this means, but this is kind of for each asset, exactly. That is the sort of the expression. So asset expressions, maybe it's kind of the idea here, right? And that will be an array NP array of like size. I want to have 3, right? So does this give me like how can I initialize just like zeros? NP zeros, okay, just NP zeros. That's what we want. Now what we have is not zeros, but we're going to have that each so we're not going to have the basically for each. Man, I'm just Python iterate Python for each for loops. Can do it like that, right? I keep forgetting these. I just keep really forgetting these. Validate Python for each. For f in paths, printf. Exactly. Or something like that. So you can have for I in range length of asset expression. You want to basically have that asset expression well, I need to define the symbols first, actually. So I'm going to define, so now I need to define for each so now I'm going to define that for j in range nq, we want to define a symbol SymPy define symbols in a loop. How do I, because I can't just declare that, so I need to be able to generate them in there. You could use functions with integer arguments to represent your constants or index variables. Here's a toy example, ABC. I just want to generate depending on the input of my tool, I need multiple variables. And okay. I'm using SymPy and I cannot find a way to replace n for the integer in the range one area with the symbols, etc. in a loop. For generate the symbols of the calculations, how can I write or call these variables conveniently in a for loop such that I don't have to write it by hand? You could use functions with integer arguments to represent your constants or indexed variables. Here's a toy example, ABC. Okay. And then equation and substitute. Okay, that's a way to do it. Essentially, what I want to So what I want to have, right, is I want to have basically 1 divided by k, or I just want to have like 1 divided by k times and now I want to kind of have the sum, which I assume that what this is, if I do 2 to the power of, and now I have these, q in here. So I guess I can build that expression inside the loop, right? That would be j, and then here we would kind of have the symbol. So where was that? Symbols. So I'm gonna have like x symbol, x symbol. How do I? I'm playing with too many things that I don't know. Symbols. I just want to define symbol. Just one symbol. Let me just say symbol. Symbol x class function, but why? That feels a bit like there should be a nicer way to define that. Define symbols inside the loop. Is there another way to? I can just do these, right? I don't need to refer, because I don't need to be able to refer to these later. So I can just I guess I can just do like these, and I can say like j, right? Now j, that would be the time step, but I also need to give it the I also want to give it the no, j will be the q, right? And I also need to give it a time step. Essentially, what this kind of resolves to is basically like these will be for loops. So what I should do is an actual I should actually do a big for loop. That says for t in range NT, kind of do the following, right? And then and now, so this will be for each t. I'm trying to build this whole equation, probably up until this point, because then we'll need to kind of add this portion of it later. Good. And now NT. And now what we need to do is we need to kind of really build that as we go, I think, to be honest. Like, really kind of build piece by piece, like, um, like I would say basically the and can I do products of matrices? So if I say of vectors, if I say like, you know, -1 of like the forecasted return, those should be defined, you know, above here, right? Forecasted return, let's just comment the whole thing out, meaning these things out. So now we're saying the forecasted returns, or just f returns. F returns is these, and so now what we do is you know, basically that'll be f returns t, right? But we need the transpose of these. So we need the numpy transpose. It's just like that. Yes, so np transpose of these times, and now here's where we're building the so wt, so that would be so we're building the equation, okay? We're not actually calculating times, and that would be basically np. Like I need to find an np array. I need to push these values in there, so the symbols in there somehow, right? So wt in this case is an np array. And then what I would do is that for n in range n, so for each asset that we have, okay, for each asset that we have, we what we want to have, what we want to do is for each asset that we have, we're going to have not a symbol, but another nested loop with the queues now. So for each asset, and then for q in nq and range nq, and now we kind of have the expression that we have here at the bottom. This one here. So now we have like and now I want to do this sum in here. Yeah. So we want to have now the okay. So now we want to have. So this would be w nt equals and now we do 2 to the power of q, right, times symbol, and now we create a symbol that is basically it's going to be x x underscore ntq. Is this the right way to? Because I would rather say qt0, whatever. Let's say let's keep the convention nqt. It's going to be easier to follow. So we're going to have the n, then it's going to have like the q, and then it's going to have the the t, and now it's going to have the q. So that's the symbol that we have, and we're adding these. Okay. So we have that. Something's missing here. Now that's just the way you define an expression, basically. So you would keep actually adding these. And basically you define that here, and you give it the value of, well, that is just 1 over k, right? That is just 1 over k. Exactly. And so then you keep adding this stuff, and so when you get out of the loop, then you have w and t. And when you get out of this loop, you basically have now you have w and t. No, and now you have wt, right? Because wt is basically a collection of these. Okay, so wt is a collection of wt is a collection of that. So wt is going to be an array of these. So what you're going to have is something like push or numpy push array append, numpy append. So np append, and you have your wt, and you're appending it the wnt. And maybe before we go ahead, I'm just gonna go ahead and print this stuff and see what happens. So print wt. Okay, it's missing a type. It's missing a type. You append it here, exactly, but it's missing a type. Expressions. So how would you handle these? What is a type? Array creation. So you got to give it a type. Can I just create like a... Oh god, okay, it's really late. Should stop. Yeah, basically, I just wanted to I just wanted to get that done. At least the first part. So now, but I know what the path is now. Can I not just create like, how can I create it? Like empty array. I'm gonna create an empty array. Can I just create an empty array? Okay, just empty. That's how you do it. Missing shape. Well, the shape is going to be basically, this is going to have like one row, and it's going to have empty elements. Strings not int. So how would you do that then? It's not a concatenation, it's a senpai concatenate int symbol or something like that. Like, how do I build these? Advanced expression manipulation. Because I like the simplicity of these. Senpai and loop. So I'm going to create it in a loop. Yeah, I'm just going to have to figure out how to work with these. Maybe I just have to do something like that. That'd be enough. String's not into string. Oh, maybe I have to maybe I should declare that as an expression. Create an empty expression. Sub-expressions you're creating. No. Oh, maybe something like that. So maybe I would something like, I would kind of keep replacing these. So SP symbol, say R, right? And then what I'm doing is I'm basically saying this is just subs. Okay, so subs. So this is like these subs. Substitute. So we're substituting x by another expression. So we're substituting r by this expression. And of course, we add another R at the end. And then we'll probably need to get rid of these last R. Does this work? R is not defined. Symbol R. So it seems I might not be able to create symbols like these. Am I? Symbol. Whatever. I gotta figure this out, so I'll double check this. I think I'll just take it over here next time. Let me just save this. I'm like just running out of time. It's really late actually, and I just wanted to kind of get that up and running. But I think that's the idea, right? So if I manage to create the full formula, then I can just query the coefficients and actually build a matrix. So that's probably the easiest way to do that. Unless there's a, I don't think there's a, because I really want to get it generic, you know what I mean? I could do a concrete example. I really want to get it generic because I want to be able to just scale these, you know, to the other cases. Yeah, cool, it's fun. I'm actually learning quite some stuff. I like that. Then stay tuned for more.